Hello everyone. Today we are going to study about the stability of dipoles and the two types of equilibriums. So, the two types of equilibrium of dipoles. Wait. All right. So this is what we are going to study about, right? So the first scenario is that the electric field is flowing in this direction, right here and here. And we have a dipole this direction. This is positive q, this is negative q. The d is very small because dipoles have very small separations. F net is 0 because they both have equal forces, that both charges have equal forces. The system has 0 force because this is in this direction, this is in this direction, right? So it is a 0 force when we calculate the net force. And the torque is also 0 because PE sine theta is 0 because theta in this case is equals to 0 degrees, or basically the perpendicular component of dipole moment, which is perpendicular to the electric field, is not present in this scenario. So yes, now moving on, if we rotate this dipole anti-clockwise by an angle theta, then we'll notice that it has the tendency to come back to its original state, right? It has the tendency to come back to its original state, and that is because the torque when we rotate it is PE sine theta, right? This is what the torque is. So what we understand by this is that if we were to rotate it anti-clockwise, it will rotate clockwise, and similarly if we were to rotate it clockwise by an angle theta 2, then it will rotate anti-clockwise. So it basically opposes whatever change we are making to it, and it has the tendency to come back to its original state. This is what we refer to as stable equilibrium. Later we are going to observe what stable and unstable equilibrium actually relate to. Now the second case is where electric field is still the same, right? But the dipole, which is signified by the direction of negative q charge to q charge, is anti-parallel to electric field vector, right? It is anti-parallel. So the positive charge is placed here and the negative charge is placed here. So in this scenario, it is still in equilibrium because F net is equals to 0 and torque is still equal to 0. But if we were to rotate it, clockwise by an angle theta, let's say, then we'll notice that it will encounter a force this way and this will encounter a force this way, and it will basically, we call these forces a couple. So this couple will provide a torque in this direction, right? So it is not returning back to its original direction. Instead, the electric field is supporting the movement that we did, right? So it is supporting the movement that we are doing instead of opposing it, instead of recovering from it. So this can be called an unstable equilibrium. It opposes the movement. It supports the movement until it reaches, the positive charge reaches this position and the negative charge reaches this position. So it basically wants it to flip, and as soon as we provide any force, it basically flips. It is an unstable equilibrium. All right, so now we are going to do the energy analysis of dipoles in both of these scenarios. So the interaction energy, we are not talking about the self energy, but the interaction energy, which is U, or potential energy, of dipoles in these cases. So in these cases, what happens is at theta equals to 0 degrees, the U is negative PE, right? It is negative PE. So what do we get by that? What do we get by negative PE? You might not be able to understand or visualize it yet, but the maximum PE that we can get is at theta equals to 180 degrees, right? This is PE, right? So this is the maximum value. This is the minimum value. What does this tell us? We have already studied it in chemistry that when the potential energy is minimum, when the potential energy is minimum, the equilibrium is stable. Stability is achieved when the potential energy is minimum. And when the potential energy is maximum, what happens is, even though it is in equilibrium still, even the minutest of interactions and the minutest of forces can turn it upside down and it will never recover again. So it basically wants to achieve minimum potential energy, and all it needs is a small push. You give it a small push from this direction, right? You give it a small push and it will go on and on until it reaches a minimum potential energy. That is what is happening here. You can relate it to chemistry and all sorts of things. So we need to keep in mind that whenever the potential energy is minimum, it is stable. Whenever the potential energy is maximum, it is unstable equilibrium. So what unstable equilibrium means is that it will never return to its original state. We can also observe this when we fix 2-point charges, right, of magnitude q, and let's say we put another charge of magnitude large q, we are not specifying what, midway through them. So what happens is, when we take it closer to any one of the charges, the potential, instead of decreasing, what happens to it is, it is given by k q by, let's call it r by 2, let's call it r by 2, right? Both of them are r by 2. Okay, so this is given by r by 2. This is the potential energy because of this, and we just double it basically. So this is what we have, plus we double it, so we get 4kq upon r, right? This is what we get. Let's say we take it to a point at r by 4. Okay, let's take it to a point r by 4. We are not going to it can be any point. We are just taking it here for simplicity in calculations. So we get kq by q upon r by 4 plus kq by q upon r 3r by 4, right? This is what we get. We do this, we get this, and then we have k q upon 4 3r. This is the potential energy that we have when we displace it here. So what happens is, it reverts back to its original position. All of these are like charges, but these two are fixed. So what happens is, it is in stable equilibrium at this position, because the potential energy is the minimum it can be. It is the minimum it can be. So it wants to revert back to this position whenever it is displaced along x-axis. Let's call it x-axis. But when we displace it along y-axis, or its perpendicular bisector per se, then what happens is, the distance between them increases. So as the distance between them increases, the potential energy decreases. So it is an unstable equilibrium when it comes to y-axis, because once you displace it in y-axis, it never comes back to its original position. So in terms of y-axis, it is the maximum potential, but in terms of x-axis, it is the minimum potential. This is a very core concept that is used in many NSEP problems, and if I'm not wrong, it has also been used in some IPHO problems. It can even include SHMs in it when the displacement is very minute. Let's say A, where A is very, very, very small than R. So it can even include SHM. But what you need to understand is that the equilibrium is stable at PE minimum and it is unstable at PE maximum, right? This is what you need to understand. So we'll meet again. Thank you for today and subscribe and follow for more. Thank you.